All right, settle in, because today we're taking a deep dive into a world that's, well, it's all around us, often invisible, yet fundamentally shaping our technology and daily lives. We're talking about inorganic materials
Yeah,
chemistry, a field buzzing with innovation and discovery.
indeed. And this isn't just, abstract theories in a textbook. It's about the actual substances that
Mm,
make up everything from your phone screen to the uh, powerful components inside a battery.
right.
Our mission today is really to demystify a pretty dense chapter from Shriver and Atkins Inorganic Chemistry,
Yeah.
make it accessible and honestly kind of fascinating for you, whether you're a college student or just curious.
Think of this as your personal shortcut, maybe, to understanding how these incredible materials get made, why they behave the way they do, and what amazing applications they lead to. We'll walk through the fundamental concepts, how solids are put together, those tiny imperfections that actually make them super performers, and even look at the future of energy storage and electronics. Ready to unlock some serious knowledge. Okay, so let's start with the big picture. What exactly is this field of materials chemistry? What's it all about?
Well, at its core, it's the study of how we synthesize, how we build new inorganic solids, and critically, how we understand and control their properties. It's a hugely vigorous field because it underpins just countless technological
Like
applications.
what sort of things?
Oh, think batteries, fuel cells, catalysts that clean emissions, advanced electronic devices. Basically, so much of modern tech, we're looking beyond simple molecules here to extended structures where atoms interact cooperatively. That leads to some really unique collective chemical properties.
And you mentioned earlier we're going beyond like perfect arrangements and fixed compositions. That seems key.
Absolutely. We often think of solids as these perfectly ordered crystals, right?
Yeah.
But actually, a lot of their most interesting behavior comes from non-stoichiometry, having slightly off compositions and the ability of ions to actually move around inside the solid. We'll build on ideas you might know, like lattice structures, but we'll add this dynamic element, things happening within the solid.
Okay, so how do chemists actually make these things? It sounds complicated.
Well, there are two main routes. First, there's direct synthesis. This often means using really high temperatures, typically, 500 to maybe 1500 degrees Celsius.
Wow, that's hot.
It is. And it's crucial for making complex solids, like that high-temperature superconductor Ybie-2Cu307. You need that heat to overcome the strong forces holding atoms together and to speed up the diffusion of ions, which is usually super slow in solids.
So we're talking about grinding stuff together, like barium carbonate and titanium dioxide, and then basically baking them for days. It's not just mixing liquids.
Exactly. It's much more involved. We can speed things up a bit, maybe using finer starting powders, pressing them into pellets, regrinding. Sometimes we even use something called a flux.
A flux.
Yeah, it's like a low melting solid that dissolves the reactants a little and helps the ions move around more easily. We also carefully control the atmosphere, maybe use an inert gas or high pressures to get specific structures or oxidation states.
Okay, that's one way. What's the other main approach?
The second main method involves solution-based synthesis. This usually works at lower temperatures.
Ah, this sounds maybe a bit more like the chemistry lab stuff I remember.
Yeah, somewhat. Many framework structures, like zeolites, those materials with tiny tunnels, they're formed by linking smaller building blocks together from a solution. We often use hydrothermal techniques, using sealed containers above the boiling point of water. The big advantage of starting with solutions is you get really good atomic level mixing. This cuts down reaction times and temperatures, and you often get smaller, more uniform particles. Sol gel processes are a good example of this.
And what if you need just a super thin layer, like for making computer chips?
Right. For that, you need chemical depositions. Chemical vapor deposition, or CVD, is key.
Mm-hmm.
Basically, you take a volatile compound one that evaporates easily containing the element you want,
Volatile.
and
Okay.
you pass its vapor over a hot surface, the substrate. The compound decomposes and leaves behind a thin film of the desired material. If the starting compound is metallo-organic, we call it MOCVD. It's absolutely critical for electronics. The challenge is designing the right volatile precursor molecules for different metals.
Amazing the different techniques. Now, you mentioned earlier that defects are super important. That sounds wrong, right? Like a defect is a flaw.
Yeah.
How can imperfections be good in materials chemistry?
Aha, yeah, it does sound counterintuitive,
Mhm.
but it's a really central idea. Okay, so all solids, unless they're at absolute zero temperature, have defects. Imperfections. These can be tiny point defects, like an atom missing, that's a vacancy, or an extra atom squeezed in, an interstitial. But you also get extended defects.
Extended defects, like
Right.
bigger flaws.
Sort of, yeah.
Yeah.
Imagine tungsten oxide, WO3. It's made of octahedra of oxygen around tungsten, all sharing corners. Now picture removing a line of those shared oxygens diagonally. The layers next to that gap can kind of slip past each other and rebond, sharing edges now instead of corners. That creates what's called a shear plane.
Oh, a shear plane.
If
Okay.
these planes are random, they're called Wadsley defects. And they mean the composition isn't perfectly fixed. You can get things like WO 2.93 instead of just WO3. But if these shear planes become ordered, they actually create whole new, distinct crystal structures, new
So
phases.
defects aren't just flaws, they can actually define the material and its properties. That's fascinating. And they're crucial for how ions move around too, right? Diffusion.
Absolutely crucial. Most solids are terrible conductors of ions at room temp. Diffusion is incredibly slow.
Yeah.
But ion movement is vital for so many things, making semiconductors, for fuel cells, sensors, catalysis.
Right.
Ions move by hopping between these defect sites. So to get good ionic conductivity, you need a few things. Low energy barriers for hopping, small ions with low charge, like Li plus or F, and really importantly, a high concentration of unordered defects. Lots of places to jump to.
Which brings us to solid electrolytes. It still feels weird, an electrolyte that's solid. Why is that so important? How does it work?
Yeah, it's a neat trick. The big drive is to get rid of liquids and batteries and fuel cells, less risk of leaks, maybe safer, more compact designs. Solid electrolytes like H2HCI4, that yttrium stabilized zirconia, YSZ, conduct electricity just by moving ions. No electrons involved in the conduction.
So what makes a solid good at conducting ions?
Well, for cationic electrolytes where positive ions move, like the silver in HCHGI4, what often happens is that at higher temperatures, the cations get disordered. They spread out over many possible sites. So in HCHGI4, above 50 degrees C, there are actually more available sites than silver ions. It's like musical chairs. They can just hop around really easily.
Oh, okay. More chairs than players.
Exactly. And for anionic electrolytes, negative ions moving like the oxygen ions in YSC, we use doping. We deliberately replace some of the ZR4 plus ions with Y3 plus favor. To keep the charge balanced, this forces the structure to create vacancies, empty spots where oxygen ions should be. These vacancies give the O2 ions pathways to hop through the material. That's how oxygen sensors in car exhausts work.
And sometimes materials can conduct both ions and electrons.
Yes, those are mixed ionic electronic conductors. Some D-metal compounds, especially certain perovskites, can do both. That's really valuable for things like solid oxide fuel cell electrodes, because the electrode needs to conduct electrons and let oxygen ions pass through.
Okay, we've covered some ground on how these materials are made and the importance of defects. Let's dive into some specific types, starting with those common metal oxides, nitrides, and fluorides.
Yes, these are really foundational. Their variety in composition and structure lets us tune all sorts of properties, electronic, magnetic, you name it.
Let's zero in on one group you mentioned, perovskites. ABX3 structure, they seem to have some really wild properties.
They really do. The classic example is barium titanate, OTO3. Picture the ReO3 structure octahedra sharing corners, but now put a big A ion, like barium, into the large central cavity. And yes, their properties can be amazing, like ferroelectricity and piezoelectricity.
Ferroelectricity, that's like a permanent electric field inside the material.
Sort of, yeah. In BitDO3, above 120 degrees C, it's cubic and symmetric, but cool it down, and the ions shift slightly off-center in the structure. This creates a net electric dipole moment. In the material, these tiny dipoles can align, creating a bulk polarization that you can switch with an external electric field. That's ferroelectricity. Makes them great for capacitors.
And piezoelectricity, that's the pressure electricity link.
Exactly. Squeeze a piezoelectric material, and it generates voltage. Apply a voltage, and it changes shape. It's used in sensors, actuators, even quartz watches rely on it. Many perovskites show this effect.
Before we move on from structures, you mentioned this idea of ligand field stabilization energy affecting where ions go. Can you break that down a bit? How does an ion's preference change things?
Right, LFSE. It's basically about how the d electrons of a transition metal ion interact with the surrounding atoms, the ligands. Some arrangements are energetically more favorable than others for certain ions. Take spinal structures, AB204. Normally you'd expect ions to go into sites based on size and charge. But say you have Ni2 plus E, which has a strong LFSE preference for octahedral sites, and F3 plus E, which doesn't really care, 0 LFSE. The Ni2 plus will grab those preferred octahedral sites, even if it means pushing the F3 plus ions into the tetrahedral sites they might not otherwise occupy. This creates an inverse spinel.
Ah, so the electron configuration dictates the structure.
In many cases, yes. It explains why we get inverse spinels, which are the basis for important magnetic materials called ferrites, and even pigments like cobalt blue. It's subtle but powerful.
And perovskites are also linked to high-temperature superconductors, right? The ones that work above liquid nitrogen temperatures.
Yes, exactly. The famous ones, like YbCO, Yb2Cu307X, are variations on the perovskite structure. They have zero electrical resistance below their critical temperature,
Yeah.
GCO, and they show the Meissner effect. They expel magnetic fields, which is why you see those cool levitation demos.
What's special about their structure?
They're perovskite-like, but typically oxygen deficient. They have these distinct layers containing copper and oxygen, often forming square planes or pyramids. It's thought these copper-oxygen layers are crucial, and you often have copper in mixed oxidation states like C2 plus and C3 plus 1, which seems essential for the superconductivity mechanism, though it's still incredibly complex.
Okay, and another wild property linked to perovskites, colossal magnetoresistance. What's that about?
It sounds dramatic, and it is. Certain manganese-based perovskites, the manganites, show this massive change in electrical resistance when you apply a magnetic field, especially near their magnetic ordering temperature.
Like how massive?
We're talking orders of magnitude, sometimes resistance drops by a factor of a billion or more. It can change from an insulator to a metal, just with a magnetic field.
Whoa. What causes that, and what could we use it for?
It's linked to a mechanism called double exchange between MnII ions. Applying a field aligns the manganese spins, allowing electrons to hop much more easily between them, switching the material from insulating to conducting. The potential is huge for magnetic data storage, think read heads, for hard drives, and potentially for future spintronics, using electron spin instead of charge for information processing. Faster, cooler computing.
And these complex oxides are also key for rechargeable batteries, like the lithium-ion ones and everything.
Absolutely. The ability to reversibly insert and remove ions, like lithium ions, into a host structure without wrecking it is critical. LiGo2 is the classic cathode material. It has a layered structure, and you can pull Li plus ions out during charging and put them back during discharging. The cobalt changes its oxidation state, CO3 plus CO4 plus, to balance the charge. Its structure, the small size of lithium, and the variable oxidation state of cobalt all contribute to the high energy density we rely on. Research is always looking for alternatives, like LiFePO4, which is cheaper and less toxic.
Let's shift from crystals to something different, oxide glasses, like window glass. What makes something form a glass instead of a nice ordered crystal?
Good question. A glass is essentially an amorphous solid bullet. It lacks long-range order. Think of it as a frozen liquid. For silica, SiO2, the reason it forms glass so easily is its network structure. You have strong covalent bonds forming tetrahedra, linked at the corners. When you cool molten silica quickly, these strong bonds don't have time to break and rearrange into a perfectly repeating crystal lattice. The local structure, the IO4 tetrahedra, is mostly preserved, but the way they connect the SiO-Si bond angles becomes disordered. No long-range pattern.
So it's like freezing the chaos of the liquid state.
That's a great analogy,
Right.
and we can modify it. Adding things like sodium oxide, Na2O, or calcium oxide breaks up the silica network slightly. This lowers the softening temperature, making it easier to work with. That gives us common soda-lime glass for bottles and windows. Borosilicate glasses like Pyrex add boron oxide, which leads to lower thermal expansion so it doesn't crack easily when heated or cooled. Glasses are used everywhere. Optical fibers containing nuclear waste, even smart windows that change color.
Okay, moving beyond oxides now. Let's touch on chalcogenides, sulfides, selenides, tellurides. How do they compare?
They often have different structures than oxides, mainly because the bonding tends to be more covalent. Sulfur, selenium, tellurium are less electronegative than oxygen. A key feature is that many D-block disulfides, like MOGS2 or TAS2, form layered structures.
Layered, like sheets stacked up.
Exactly. You have layers, maybe a metal layer sandwiched between two chalcogen layers like AXP. The bonding within these sandwich layers is strong, but the forces between the layers are often weak, just van der Waals forces. That's why MOS2 is such a great solid lubricant. The layers slide past each other really easily.
And these layered structures are good for intercalation. What is that exactly?
Intercalation is when you insert guest atoms or molecules between the layers of a host material. The host structure itself doesn't fundamentally change. You're just stuffing things into the gaps, the van der Waals gaps. Think of sliding lithium ions between the layers of graphite in a battery or between the layers of MOS2. Often, the guest donates an electron to the host layers, and the resulting ion sits in the gap. The key is that it's often reversible. You can put ions in and take them out. That's fundamental to how many rechargeable batteries work.
Interesting. Now, what about framework structure? Zeolites came up earlier.
Right. Frameworks are built from linking polyhedral units, often tetrahedra, like SO4 or AO4, or sometimes octahedra, into a continuous 3D network that usually contains pores or channels. Zeolites are the classic example of luminosilicates with very well-defined pores. Synthesizing them is quite sophisticated now. Chemists use organic template molecules to guide the formation of specific pore structures.
And they're used for way more than just detergents, right?
Oh yeah, they act as molecular sieves, separating molecules based on size, because only molecules small enough can fit into the pores. They're great ion exchangers, which is the detergent application removing Sig2 plus and Mg2 plus from hard water, but also used for cleaning up radioactive waste. They're used as catalysts too. And there's a related class, aluminophosphates or ALPOs, built from AlO4 and PO4 tetrahedra with similar uses. And then there are metal organic frameworks or MOFs.
MOFs, they get a lot of buzz. What's the concept there?
MOFs are really cool. Instead of just inorganic building blocks, you use metal ions or clusters connected by organic linker molecules. These linkers bridge between the metal centers, creating extended, highly porous 3D frameworks. You can design the linkers and metals to get incredibly large pores and enormous internal surface areas, like the surface area inside 1 gram could cover a football field.
Oh, what's that useful for?
Gas storage is a big one, storing hydrogen or capturing carbon dioxide. The high surface area means lots of places for gas molecules to stick. Also catalysis, separations, and even drug delivery, loading drug molecules into the pores and having them release slowly.
Let's switch gears to energy again. Hydrides and hydrogen storage. What's the state of play there?
It's a major challenge for a potential hydrogen economy. How do you store hydrogen safely, compactly, and reversibly? Compressed gas tanks are heavy and bulky. Liquid hydrogen requires extreme cold. So researchers are looking at materials that chemically bind hydrogen metal hydrides.
Like magnesium hydride.
MgH2 is a good example. It stores a decent amount of hydrogen by weight, about 7.7%, but you have to heat it pretty high to get the hydrogen back out. People are trying things like doping it or grinding it into nanoparticles, ball milling, to improve that. There are also complex hydrides, like alanates containing AlH4 or borohydrides, BH4. Something like LiBH4 stores a huge amount of hydrogen, over 18% by mass, but getting it in and out reversibly and at reasonable temperatures is still really tough.
So chemical storage is tricky. What about just sticking hydrogen onto surfaces?
That's the other main approach, physisorption. Using materials with very high surface areas, where hydrogen molecules just physically absorb, stick weakly onto the surface or inside pores. Things like activated carbons, carbon nanotubes, certain zeolites, and especially those MOFs we just talked about, are candidates. They can hold significant amounts, but often you need very low temperatures or very high pressures, which add complexity.
Okay, from fuels to aesthetics.
Yeah.
Inorganic pigments, the things that give paint its color.
Exactly. These are intensely colored inorganic solids used in paints, plastics, ceramics, cosmetics, you name it. Their big advantage over organic dyes is often stability. They don't fade as easily in sunlight, and they can handle higher temperatures. People have used them for millennia, think Egyptian blue.
How do they get their color? What's the chemistry?
There are a few main mechanisms. For many transition metal compounds, it's D-O-D transitions. Electrons hopping between d orbitals within the metal ion absorb certain wavelengths of light, and we see the complementary color. Cobalt blue, Col-L2O4, is a classic example. Another is charge transfer. An electron jumps either between a metal and a ligand or from the valence band to the conduction band of the solid. Cadmium sulfide, CdS, is bright yellow due to this. Cadmium selenide, CdSe, is red. The band gap determines the color. You can also get intervalence charge transfer in mixed valence compounds like Prussian blue with both Et2 and Fe3, where electron hopping between the different iron sites gives intense color, and sometimes it's trapped inorganic radicals like the S3 ion in ultramarine blue.
And the non-colors, white and black.
White. For white, the absolute champion is titanium dioxide, TiO2, usually the rutile or anatase forms. It's brilliant white because it scatters light incredibly effectively. It has a high refractive index, it's non-toxic, stable. It's in almost all white paint, paper, plastics, even sunscreen and food. For black, the workhorse is carbon black, essentially very fine soot from burning hydrocarbons. It just absorbs light across the visible spectrum really well. There are other specialty pigments too, of course.
All right, let's turn to the heart of the digital world, semiconductor chemistry.
The foundation of all modern electronics. Semiconductors are materials with an electrical conductivity between that of a conductor and an insulator. They have a crucial property called a band gap. These materials often involve p-block elements,
Yeah.
especially group 14 like silicon and germanium, or combinations like group 13-15 or 12-16 compounds. The specific elements determine the size of the band gap, which dictates their electrical and optical properties.
And silicon is king here, right?
Pretty much. Crystalline silicon from group 14 has a band gap around 1.1 electron volts, perfect for many electronic applications. Germanium's is smaller, diamonds is much larger, making it an insulator. Pure silicon isn't a great conductor, but its power comes from doping, adding tiny, controlled amounts of impurities. At a group 15 element like phosphorus, you get extra electrons, that's n-type. At a group 13 element like boron, you get holes where electrons are missing, that's p-type. This doping drastically increases conductivity and allows us to create p-n junctions, the basis of diodes and transistors. Amorphous silicon, often used in solar cells, has a less ordered structure but absorbs light well.
And there are other semiconductors that mimic silicon electronically, isoelectronic systems.
Exactly. Compounds that have the same average number of valence electrons per atom. Group 13-15, or semiconductors, are really important. Gallium arsenide, PAAs, is a classic. Electrons move faster in GAs than in silicon, so it's used for high-frequency devices like in cell phones and satellite communication. Gallium nitride, GaN, is another huge one. It has a wide, direct band gap, which makes it perfect for emitting blue and green light efficiently. That led to blue LEDs, white LEDs by adding a phosphor, and Blu-ray lasers, a revolution in lighting and data storage. You also have group 12-16 semiconductors like zinc sulfide, ZNS, or cadmium telluride, CDT. CDT is a major material for thin-film solar cells.
Okay, to wrap things up, let's look at molecular materials and fullerenes. This sounds like blending molecules with solid-state properties.
That's exactly the idea. Trying to use the design flexibility of making individual molecules to create bark materials with interesting collective properties. Let's start with fullerenes.
Based on C60, the buckyball.
Right. Solid C60 itself is just spheres packed together, interacting weakly. But when you intercalate alkali metals into the structure, making compounds like K3C60, things change dramatically.
They become superconducting. How does adding potassium make C60 superconduct?
It's fascinating. K3C60 becomes superconducting around 18 Kelvin. If you use larger alkali metals like rubidium or cesium, the transition temperature goes even higher. The alkali metal atoms donate electrons to the C60 molecules and sit in the gaps, the tetrahedral and octahedral holes, between the buckyballs in the crystal structure. This changes the electronic band structure, allowing superconductivity. It shows how discrete molecules can form solids with remarkable electronic properties. And this leads into the broader field of molecular materials chemistry.
So building solids from carefully designed molecules.
Yes. The goal is to control the solid-state properties by controlling the structure and interactions of the molecular building blocks. For example, you can make one-dimensional metals. Stacks of square planar platinum complexes can conduct electricity along the stack direction because the metal diporetals overlap. Though interestingly, a perfect 1D metal is unstable at low temperatures due to something called a Peersall's distortion. It prefers to distort slightly and open up a small band gap. We can also design molecular magnets.
Molecules that act like tiny bar magnets.
Sort of. You can have molecular solids where the magnetic moments on individual molecules or ions interact to give bulk magnetic ordering, like ferromagnetism. There are even single-molecule magnets, SMMs, individual large molecules, often clusters of transition metals like manganese that retain their magnetization below a certain temperature. Huge potential for data storage if you could figure out how to address them individually. And you can even make inorganic liquid crystals. Metal complexes designed to be rod-shaped or disc-shaped can form fluids that are fluid like liquids, but retain some degree of molecular alignment, like conventional liquid crystals. These could combine the display properties of liquid crystals with the electronic or magnetic properties of metals.
Wow, what an absolutely incredible journey. From, those high-temperature furnaces making oxides to the really delicate dance of electrons and molecular magnets. This deep dive really shows how intricate, how interconnected, and just how fundamentally impactful inorganic materials chemistry is.
Indeed. We've seen how everything from the synthesis method to even those tiny, seemingly insignificant defects and the precise arrangement of atoms dictates a material's properties: electronic, magnetic, optical, mechanical. It's the science behind durable pigments, the fastest computer chips, efficient solar cells, powerful batteries, and maybe even materials to store hydrogen for a cleaner energy future. It's truly at the forefront of innovation.
So, what does this all mean for you, the listener, the learner? It means that getting your head around these fundamentals of solid state chemistry, it isn't just, academic box ticking, it's genuinely empowering. It gives you a lens to really see the science humming away inside the technology that surrounds us every single day. It helps you understand how things work.
And it definitely raises a big question, doesn't it? As we get better and better at designing and controlling materials at the atomic level, what completely unimaginable applications or even fundamental new scientific discoveries are just waiting around the corner? What will the next generation of chemists, perhaps some of you listening, unlock?
That is a thought-provoking way to end our deep dive. Thank you so much for joining us on this exploration of inorganic materials. We hope you feel a little more clued in and maybe, just maybe, a lot more curious. Until next time, from the entire Last Minute Lecture team, keep digging for knowledge.